Okay, so we are talking about how to find the slope of a function at one particular point. Okay, I'm not going to rehash all the stuff that we've been doing. I feel like we're pretty solid on all of that. You could also say that that is the slope of the tangent line. And yesterday we also went that extra distance of not only finding the slope at that one point, but we even found the equation of that tangent line, and that's helpful for lots of different reasons. Do we have any evidence of the work that we did here? Yeah. So what we mentioned yesterday and sort of alluded to is, I said, you know, what is the slope at this point? And we all did the work and we did it all through. And then I said, what's the slope at this point? And we plugged it into the formula and did all the work. And I said, what about at this point? You do it as a table and you did all that stuff. And you know, we could continue to play that game, and it's a lot of algebra. It's not that difficult, but it is kind of tedious. And I said, okay, looking ahead, what if, instead of me telling you this point or this point or this point, what if I just said, of some generic point x, find what the tangent line is, okay? And I'm not going to tell you what x is, but you just kind of use it as a placeholder. And you say, well, I'm not going to know what the actual value is. I'll just end up with another formula. And I say, yeah, that's fine. But then when I tell you, I want you to find the slope at -3, then you'll just plug in, or +3, then you'll just plug in +3 into whatever formula you came up with. Or you'll plug in -1, or you'll plug in 0, or you'll plug in 5, or 2, or whatever. Does that make sense? Okay. So what we're looking for here is the generic slope of the tangent line formula. Okay? So I'm going to go all the way as far over. All right. That's what happens when I insert all the other slides today. So today, the topic or the title, I guess, is 3B, the derivative as a function. That's where we're going with all of this. The derivative as a function of x. We're trying to make the derivative into a formula. So the question is, what if I want to find the slope of f of x equals x squared plus 1 at x equals -3, x equals -2, x equals -1, 0, 1, 2, and 3. I want to find the slope at all those points. And that sounds like that's 30 minutes right there. Plug it into the difference quotient limit. You see what I'm saying? Plug it in for this one, plug it in for this one, get it all over here. Okay? And say, no. The answer is find the slope for x, then plug in these values. So the slope of the tangent line at x is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So now when we do this, instead of plugging in a number, plugging in -3 and plugging in -3 right there, I'm just going to plug in x. Okay, there, just did, plugged in x. Okay? Nick, does it kind of make sense what we're doing here? So we're going to follow those same sort of steps that we did before yesterday, that we did it like 3 times, and then we did it on the example, and then we started doing it on the other one. Only it's going to be all algebra. So it's going to be like lots and lots of letters. So here we go. So if you remember, I'm now going to do just a pre-calculus step, x plus delta x. Yeah, it's amazing. Those little small little things kind of help you remember. But that's what we do. Plug it in, right? Okay. So the slope of the tangent line is the limit as delta x approaches 0. Emily, we're recording, right?
Yes.
Okay, great. So I'm going to plug in x plus delta x every time I see an x. So that's going to be parentheses x plus delta x squared plus 1 minus, and then in the place of f of x, I'm going to put brackets here for the whole thing. I'm going to put x squared plus 1 all over delta x. And then we're just going to play the same game that we played before. So we know this is an a plus b squared situation. So the answer is going to be a squared plus 2ab plus b squared. So the first thing squared plus 2 times the first thing times the second thing. So 2 times x times delta x plus, I'll put the delta x in parentheses and square it. At the same time, I'm going to distribute that minus sign right there. So minus x squared minus 1 all over delta x. I missed something, didn't I?
The plus 1?
Yes, I missed the plus 1. This plus 1 right here. I'm going to put it right here on the end. And we'll combine my terms, minus 1 plus 1. They're gone. Anything else?
X squared minus x squared.
Yeah, x squared minus x squared. So now I have the limit as delta x approaches 0. Let's see if you can do two things at once. We've done this enough times, I think. Notice I have a 2x delta x and I have a delta x squared. So, once again, as always, we'll factor out a delta x. And I'm left with 2x for the first term plus delta x all over delta x. And I mean, this kind of makes sense because we saw this happen like 3 times, the same exact thing, you know? So, the only thing is we just had like some numbers in there. Delta x cancel, so that slope of the tangent line is the limit as delta x approaches 0 of 2x plus delta x. Well, that's kind of interesting. Will direct substitution work now?
Yes.
Yeah. Just plug in 0 for delta x. So the slope of the tangent line at x is 2x. Okay. So that would mean, so at x equals -3, the slope of the tangent line is 2 times -3. -6. Let's see if that makes sense. At -3, we're saying the slope of the tangent line is -6. Would y'all agree with that statement? Kind of look realistic? This is the function, right? Y equals x squared plus 1. What about at -2? At x equals -2. Slope of the tangent line is?
2 times
Which is? -4. Over here. I'm just going to put there's a -6, this -4 for the slope. Is that realistic for the slope of the tangent line there? Why are you nodding your head? Yes, Chloe.
Looks right.
Okay. Why does it? Elaborate on that. Why does it look right?
It's going downhill.
going downhill and then also relative to the other one, right? If this is -6, which is super steep going downhill, this one is -4, it's not as steep going downhill. So the numbers actually kind of match reality, thank goodness. What about x equals -1? What's the slope of the tangent line? 2 times -1, so that's -2. I should put m tangent, but whatever. Slope of the tangent line. What about at x equals 0? Didn't we figure that one out yesterday?
Yeah, it's 0.
And you know what? It's 0 based on our formula as well. So here's a question, class. Which would you rather do? Would you rather do each one of these individually and kind of have some numbers with it? Or would you rather do it one time, kind of annoying with variables, but then be able to just go boom, 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 boom? Kind of like this a little bit better, right? And why stop there? What's the slope at x equals 1? 2 times 1, so that's 2. What about at 2? 4. What about at 3? 6. Look how good you all are. And that matches reality, right? 2, 4, 6. It's getting steeper all along the way. Okay? So what we have there, that m tangent equals 2x, that's a formula, right? And what does that formula depend on? That's not exactly what I'm going with. What I'm getting at is it depends on x. Okay, right? It depends on where you are. Okay? So we would say that the in our language we would say that the slope depends on x. What's more, it's more than just a depends on x. It's actually, for any given x, you're going to get one and only one value of the slope. In mathematics, we have a formal definition for that relationship, and we say it's a function. We would say that the slope is a function of x. Remembering that functions have a one input, you get one output relationship. If you have one input, you get two outputs, then it's not a functional relationship. Okay? We had up here f of x equals x squared plus 1. We have this new thing, this new formula, which is 2x, okay, which is the slope of the tangent line, and we have a notation for that. But we can't say f of x because f of x is already taken. So we say f prime of x. F prime of x is equal to 2x. And what this refers to is this is the formula for the slope of the tangent line. That little tick mark right there, I'm not drawing it in the proper location really. It's really more like F. And the prime is kind of in between there. And you say prime, it's a single tick mark with an apostrophe. And this notation and this concept is so important that we have a specific name for it, and it's called the derivative. This is the derivative function. Or the derivative. That's what f prime is. The derivative of f is 2x. So the derivative is a formula which is going to give you the slope of the tangent line at any point. So just to kind of make it a little bit more obvious, I wrote all of this out in proper mathematical notation. We would say f prime eval evaluated at -3 is equal to -6. F prime evaluated at -2 is -4. F prime, I'm just going to 0, 0, and so on and so forth. So what I this notation right here is exactly the same as this long story over here. At x equals -3, the slope of the tangent line is equal to -6. But we shorten all that down to just say f prime -3 is -6. But as calculus students, you need to be aware of that when I'm writing this, what I'm meaning is this. Okay? I mean the slope of the tangent line. Okay? Alright, this is huge. I can't make a big enough deal out of this. So, if we're looking for a formal definition, we would say f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Before, what we had was that this right here equals the slope of the tangent line. So I guess I'll allow that. I mean, it's also m tan. Sometimes you will also see, instead of saying f prime, they'll say dy over dx. That's another notation. This is alternate forms. Dy over dx equals m tangent equals. Sometimes we'll say d over dx of f of x equals. The way you would say this out loud, you'd say the derivative with respect to x of f of x. Notice I'm not putting the little prime mark in there. I'm putting the original function in there. I'm saying the derivative of f of x is equal to this. All right. Let's go ahead and do another one together. Maybe maybe we'll do a parabola that opens downward. So we'll say find f prime of x using the definition of the derivative of f of x equals negative x squared minus 2. And we'll say then evaluate at -2, -1, 0, 1, and 2. So find f prime of x using the definition of the derivative of this function, and then plug in this, and this. Let me get you started, then I'll let you work as a table. All right? So, remember that we'll just write down the formula. F prime of x equals limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Somebody tell me what the next step would be. What's that? Plug in, plug what in? To where? Okay, plug in x plus delta x into that. Then you'll have the minus, and you'll have, put minus in the brackets like I did, and put that whole thing over here. And then you'll just do the algebra, and you'll simplify it all the way down. until you get just a function of x, and then you'll plug those values in. Okay, I'm gonna let, about 3 minutes probably. Go ahead. Make sure you make that negative is out in front. Make sure you all don't make a mistake right off the bat. Negative x plus delta x squared.
Actually, I do have one question.
Okay.
So since it's a negative x squared, I'm like factoring out a negative delta x.
Okay.
So would that make my negative delta x squared positive, like the other one that I'm leaving in the parentheses? Since I already factored out.
I wouldn't factor out a negative delta x, so just factor out a delta x.
Okay.
Alright, look around, saw some good stuff. That negative out front, x squared plus 2x delta x plus delta x squared minus 2. A minus and a minus is a plus x squared. A minus and a minus is a plus 2. Now this minus right here gets pushed in front then of each one of these items. So that's where you might make a mistake here. So we have minus x squared plus x squared. They're gone. Then minus 2x delta x. Then minus parentheses delta x squared. And then that minus 2 and that plus 2 cancel. Does that make sense now?
That's wrong.
That's wrong?
No, that's where I'm at.
That's where you're at, okay. Suggestions on where to go next?
Well, the delta x out of both.
Yeah, that seems pretty familiar. So minus 2x, and then we still have a minus delta x over here. Oh, delta x still next to x, and then at this point we just do direct substitution. That goes to 0. So we have f prime of x is equal to negative 2x. Alright? So let's plug in some values. So f prime of negative 2 is going to be negative 2 times, plug in negative 2, so we have 4. Let's go over here. I've drawn negative x squared minus 2. It's a parabola opening downward, and it's also shifted downward. Can you all see that okay? So at negative 2, so before, what do y'all think? Does that seem realistic for the slope of the tangent line right there? Chloe's nodding her head yes. Cody says?
Not compared to the one up there.
Not compared to the one up there. Elaborate.
I think you just, the lines are,
You're saying that this 2 doesn't line up with that 2?
yeah, well, no, I mean like,
The slope.
just the way you drew the line to demonstrate it.
One of the slopes is like this, the other one's kind of
Yes.
like that.
Okay, well this slope is negative 4, right? So if you're standing right here, always looking this way, you're downhill. And if you're standing right here, is that a positive slope or negative slope?
Yeah, but I'm still saying it looks steeper than the other one.
You're saying that this one looks steeper than that one looks.
I think
a
you just
steeper
drew,
upward rather
you
than-
just drew the line.
Oh, okay. Yeah. Okay. So you're saying that this one. Okay. Yeah. Okay. I thought you were saying that this one should look like that one. Right. Well, I want to make sure that you understood that this is a positive. No,
Yeah,
this is a
I
negative.
get that.
You're telling me that this one. Yeah, what I know what you're saying. It's not a. It's not a perfect vertical reflection. Yeah. Okay. I'm comfortable with that. All right. -1. Negative 2 times negative 1 is going to be a positive 2. Looking at the graph, yeah, it's definitely positive right here on the parabola, and it's definitely less steep than the 4, and we're not going to pay attention to anything above the x-axis, though I would say it's not too bad. Negative 2 times 0 is 0. That's kind of interesting. It's also interesting to me, though, that these are the same values, even, just negative. Negative, negative, positive. And so then at 1, negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. And we can see that that's kind of matching up with that. Can you all start to kind of see maybe the value of calculus that you do at one time, you do this manipulation one time, and then you can plug it in here, 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 here? Okay. Yeah, absolutely. I think there's some real neat value there. Okay. So what we're gonna do tomorrow and the next days, we're gonna look and see there's some patterns here. Quadratics tend to have a pattern when it comes to their slope values. Linear functions have a pattern when it comes to their slope values. Cubics, all of those different things do. So Hector, I'm going to pick on you for a second. You have the opportunity of not falling into a trap that I have other students fall into a trap every single year. Okay. So see if this makes sense to you. All right. When I say -6 right there on this function, okay, what am I saying is -6?
Where the dots are.
Right, help me out here. Stephanie, what am I saying is -6? What about that dot? The slope of the tangent line is -6. Okay? Now, that was at x equals 3, right?
Mm-hmm.
What is the y value there? No, it's not 6. The y value, I'd have to plug it into this formula here. x squared plus 1, so negative 3 times negative 3 plus 1, so that's going to be a value of 10. Okay? So every year I have students mix up what these numbers mean. Okay? F of negative 3 is 10. It means what is the y value when you plug in this x value? And it's going to give you the how high up or how far down you are. If it's positive, you're up above the x-axis. If it's negative, you're down below the x-axis. Okay? So that's going to give you the y value. F prime of negative 3 equals negative 6 is giving you the slope value. It seems really obvious now, but every year I do have students that run into some issues with that. That they end up putting the slope value when they should have put the y value, or the y value when they put the slope value, stuff like that. Just want to make sure, obviously with this notation is pretty clear, f prime, that's going to give you slope. But anyway, so stuff like that, so just keep this in mind, okay? All right. I think that's pretty good. There are some alternative forms. Okay, yes, I need to make a note of some other things that you read about. So, we just talked about this function right here. F of x equals x squared plus 1. And then we found the derivative, f prime of x, which equals 2x. So, how do I put this? I'll just put the sentence down here. Well, here's my question. Is that function right there continuous? Yes or no? Yes, it is continuous. Now you have to ask the question, is this function differentiable? Question. Is this function differentiable? Namely, can you take the derivative of it? As it turns out, the answer is yes. Answer, yes. And in fact, we did take the derivative of it. It's 2x. That other function we had, negative x squared minus 2, that function was continuous. And it was differentiable. When I say it's continuous, I should say it's continuous everywhere. Okay? And it was differentiable because we found the derivative was negative 2x. Okay? What's interesting is the relationship between these two properties, a function being continuous and a function being differentiable. Okay? And it's backwards what you might think. Here's the point. If a function is differentiable, then it is also continuous. If a function is differentiable, then it is continuous. Alright? Now let me try to build this from the ground up here. Continuous, if you remember, that's sort of like going to be like our foundation. What does continuous mean? What are some of those things, the informal definition that we said?
No jumps.
No jumps, no breaks, no gaps, no holes, no asymptotes, all that stuff, right there, right? So, no jumps, no holes, no asymptotes, stuff like that. imagine if there was a function that did have those things. Imagine the function that had like a jump, right? And I would say, all right, or maybe a gap or something like that, okay? And I said, what's the slope of the tangent line at that point right there? And you might say, oh, that's no easy. That's no big deal. It's right here. And I would say, well, no, not really, because if I apply our method of finding the derivative, remember our method of finding the derivative was a limit process, and put a dot here, put a dot here, draw a line, put a dot here, put a dot here, draw a line, put a dot here, find this slope here. You see what I'm saying? Our secant lines are not approaching the tangent line that we think it would be horizontally. Okay? So, and the same thing if there was a gap, the same thing would happen if there's an asymptote. We wouldn't be able to meaningfully talk about the derivative there. Okay? So, in order for you to be able to find the derivative, so differentiable. In order for you to be able to find the derivative, you have to be continuous. So what I'm saying is that they're continuous, yes, okay? Then you have the possibility of being differentiable, okay? So, if you tell me, I have a function that is differentiable, then I'm like, aha, you've actually told me two things. Because if it's differentiable, then I automatically know it has to be continuous. Now, just because it's continuous doesn't mean that it's differentiable. You're like, ooh, that sounds interesting. Can you give us an example of a function that is continuous but is not differentiable? And the answer is yes. I will give those examples to you tomorrow. Okay? So we'll write that down and save this document so don't forget. And you can write it down too, so you don't have to push it down. Well, is it possible for a function to be continuous but not differentiable? In other words, what we're talking about is like situations that are what I would call sort of like on the edge here, like border cases. They meet the continuous check mark, criteria, but they don't meet the differentiable criteria. So we will answer that question tomorrow. Tonight's homework is going to be a team effort. Okay? I have 10 functions, okay, that I want you to do the derivative of using the long way. But it's going to be a team effort. So y'all are going to do, so everyone's going to do like 2 of them. That's not too bad, right? And then tomorrow we'll come back and share what we've discovered. So you don't have to do all of them. You just have to Oh, did I not give you one, Jeremy? All right. So I'm going to tell you, I'm going to assign them to you, and you're going to circle which ones that you're going to do. Rosa, which one would you like? Rosa wants 4. Okay, and one more.
5, I guess.
She's going to do 4 and 5. Hector, which one would you like? 1 and 2. Chloe, which one would you like? I should give you one chance, and then you should go around again. What am I thinking? Go ahead, Chloe. Pick one.
6.
Okay. Stephanie, pick one.
8.
Jeremy, pick one.
9.
Cody, pick one.
9. 7 been picked?
7 has not been picked. Emily, you're 3.
Yeah.
Nick, you're 10. Is that everybody? I think that's fair. Since you get picked first, have to do 2 of them. Last, just have 1. You only have 1 homework problem tonight. That's today is Wednesday, so yeah. Oh, it says 2 questions, 3 more questions. So all of 3A is due tomorrow, and then 3B, your 1 question. Be prepared to write up here on the board, or have me peek over behind you with the camera, and then it gets displayed on the application.